Hello and welcome to section 4.3 Riemann Sums and Integrals. We're going to be talking about a lot of this in class, so I just kind of wanted to introduce you to this process. Basically what Riemann had said is that there is a relationship between the definite integral, which would look something like this, and the summation that we have been doing with a limit. And he used a little bit different notation than what I'm going to use, but the limit of our summation from I to n of our function f of x, delta x. And so he's saying that there's a connection between these two, and so we're going to talk about that connection in this example. And so we're going to go ahead and do the integration of this through the limit process. And so we're going to say the first thing we need to find is what delta x is, and delta x is going to be b minus a, which would be ends up giving us 1 minus negative 2 over n, which is 3n. So that's our delta x, and that's what's going right here. And then remember that this gets a counting number I for the f of x sub I. And so just like we practiced in our previous section, we are going to use our summation and our limit as n goes to infinity. When we plug in 3i over n, well, we have to take into account that we're not starting at 0, that we're starting at negative 2. So that's going to go into our function. Well, our function is 2 times x. And so 2 times this x sub I, which is really negative 2, plus 3i over n. The 3i over n is our counting number that we got when we were dealing with our delta x. And our negative 2 is where we're starting from at the bottom of our integration. So I get this. So this is my f of x, and then that gets multiplied by my delta x, which is 3 over n. So with a little bit of algebraic manipulation, you can see that 3 over n times 2 would give me 6 over n. So I can, since it's that's a constant, I'm going to factor that out. And so out of my summation, it's going to be 6 over n, and then I've got my summation. And then I'm really left with negative 2 plus 3i over n for that part. And so at this point, I can go ahead to drop my summation. To drop the summation part, I can use my summation formulas that we learned in the previous section. And so let's see, if I remember them correctly, we end up with 6 over n. That's the factored out. 2 is a constant. When we do a summation of a constant, we're going to take negative 2 n number of times, and then we have 3 over n, and then we multiply that times our I factor, which I believe was n times n plus 1, all divided by 2. And so replacing that 3 over n, or that 3 over n times this thing, we can do a little bit of simplification, make our life a little bit easier. And so so at this point, we've done all the calculus we're going to do. Now it's just a matter of simplifying this before we take the limit and do some more calculus. But I'm going to say 2n. And then here, let's see, n's can cancel out, so it looks like I'm left with plus 3 times n plus 1 all over 2. And finally, I will end up with a limit. If I was to, before I take my limit, multiply all of this through, I'm going to get negative 12. And then, let's see, I'm going to get 18n over 2n. And one more here. Let's see, I should probably just do this 3n plus 3 over 2. And then this guy would turn into another one. Let's see, I'm going to get plus 18 over 2n. So before I take my limit, I could simplify that a little bit. And sorry if it's a little bit strange. This is negative 12 plus 9. And then here I've got 9 over n. And so as I take my limit to infinity, Well, the constants remain as they are, and so I get negative 12 plus 9, and then remember when I do a limit to infinity, I'm dividing by infinity. That's a 0. So my final answer for this, the integration from negative 2 to 1 of 2x dx is negative 3 when I simplify that. So that's the area, and you can see by the picture up here that there's more area under the x-axis than over the x-axis, and when there's more area under, you get a negative area under the curve. And so then my next example that I'm going to deal with is finding, we're going to sketch the region of each curve, and then we're going to evaluate the integral as best we can. And so what we have here is that in the first function is a constant. So we're integrating from 1 to 3 of 4, and so we're basically just looking at like a rectangular shape, which means it is 4 by delta x, which would be 4 times 2 in this case, because the area of a rectangle is 4 times 2, so we have an area of 8 units of whatever it may be. And so some of these shapes you can kind of see are going to be standard shapes that we know and can actually find the area of. And an example here, we have a trapezoid. So if I don't need to find the area under the curve for this. I mean, I am, but I can treat it as a trapezoid. Base 1 down here is 2. So remember, the area of a trapezoid is 1/2 base 1 plus base 2 all times the height. And so to find that area, my base 1 looks like it is 2, my base 2 looks like it is 5, and the height is the distance between the two bases, which looks like it is 3. And if I crunch those numbers, I end up with 21 over 5 for the area of that curve. And so don't forget, that's really all we're doing for these. And so this last one is this is the square root of this thing, which is 4 minus x squared dx from negative 2 to 2, which gives me this half circle. And if I remember what the area of a circle is, or at least half of a circle, it's 1/2 pi r squared. And so if I take 1/2 pi, and my radius in this case looks like it is 2, so I'm going to square 2, which will give me 2 pi as the area of that. And so again, if you can take the area of it without going through this whole Riemann sum thing, you can do that. We're going to talk more about the connection between these in the next few days. So please come class prepared. If you have any questions, please ask.